During the mid-1900s, Einstein had long been dreaming of a unified physical theory. This was a theory that would explain all forces within our universe. Born in Germany in 1879, he is recognized for his discovery of special and general relativity. These massive breakthroughs explained the behavior of the universe and restructured humans' understanding of light and gravity. But his mind was not yet put at ease. Many mysteries and strange paradoxes of a field known as quantum mechanics remained. Einstein tried to evade the implications of the subject for the whole of physics, although this did not prevent him from thinking about it. The quantum mechanical realm deals with the properties of atoms and subatomic particles. Unlike classical physics, which is associated with direct observation and complete determinism, quantum mechanics deals with probability. The two known fundamental forces at this time were electromagnetism and gravity. Quantum electrodynamics, or QED, was being created as a way to establish electromagnetism on a quantum level. Meanwhile, Einstein's breakthrough with gravity, summed up in his general theory of relativity, dealt with classical physics. A new theory on quantum gravity was needed. Fast forward to the late 1960s, multiple great physicists stumble upon a new model called string theory. Gabriele Veneziano, an Italian physicist, wrote a paper attempting to explain the strong interaction, one that confines quarks into protons, neutrons, and other hadron particles. His paper was celebrated among scientists, but an apparent link to his proposed model and strings, or quantum gravity, was not made until the 1970s. Before proceeding with an explanation of string theory, let's solidify our understanding of the important subatomic particles that will be referenced. Here we have an atom with a cloud of electrons swarming the protons and neutrons within its nucleus. Protons and neutrons, in turn, are composed of smaller particles known as quarks. Quarks almost always come with antiquarks in pairs or triplets. These combined quarks make up the hadron. All particles are classified into either fermions, like electrons, protons, and neutrons, or bosons, force-carrying particles like the photon, based on their individual spins. Hadrons, meanwhile, can be either fermions or bosons. Baryons and mesons are two types of hadrons that can be distinguished by their number of quarks. Earliest version of string theory was known as bosonic string theory and included only bosons. Later, superstring theory was created, which incorporated both fermions and bosons, as well as an idea called supersymmetry. Many versions of superstring theory were developed, which were combined into M theory. The main idea is that these particles are modeled as one-dimensional strings. These strings' vibrational states theoretically correspond to various particles, such as the graviton, which would carry the gravitational force. You probably find it familiar to think of everyday life as three-dimensional, width, length, and height. Einstein's general relativity even incorporated time as a fourth dimension. The mathematics of string theory requires 10 plus dimensions. Bosonic theory was thought to be 26-dimensional, superstring theory 10-dimensional, and M theory 11. So you may be asking yourself how all of these dimensions are possible. There are two scenarios that have been thought up. One of these is compactification. This entails that the extra dimensions are essentially coiled up so that they cannot be viewed. Imagine a rod or a wire. From far away it may appear one-dimensional, but once you come closer, the circumference reveals itself. The extra 6 dimensions can be compactified into something called a Calabi-Yau manifold. Let's discuss the brain-world scenario. Brains are masses that can be of many orders or dimensions. Some scientists have proposed that our own universe is a 3D brain within a larger dimensional space. Think of a curtain or paper, 2D objects in a 3D space. One kind is the D-brain, which is distinctive because it is attached to open string ends. Particles that are confined to the brain do not need to hold extra dimensions, even if they exist. All sorts of fundamental particles could be stuck on the brain, but not when it comes to gravity. Gravity would exist within the expansive geometry of space.